Let's do some magic today. Let's run Haskell. In the previous video, we talked about fixed point combinator. And actually, in Haskell, there is such a function. I think it's defined somewhere, but interesting that we can define it by ourselves. So this said that this was Y combinator. And what it do? It takes absolutely any function and return to us its fixed point. How can this be? Think about this. You have any function and you have some function which know nothing about any function you will give to it, and it somehow produce to you a fixed point. So how can we write this? Our function y takes some function f, and what we have? By the definition of the fixed point, so we go into somehow recursive definition here, and we can write this as, let's take our function f and take our fixed point. So exactly, now I take it from anywhere. So I want to have a fixed point, and I define this function y. This function y takes this function f, and how can I find for any possible function its fixed point? Okay, I say, hey, you have this function f, and I have this function y, which will find me fixed point. Okay, let's put it into this function f, and it will receive me this fixed point. Let's try. And we can see that compiler take this thing. Now let's review this type signature of y function. Here we can see it has following type signature. It takes some function from a to a. Here we can have absolutely any types, and as a result we will have this fixed point. Do you feel intuitively that something wrong with this? There is some magic or some strange things happens. For example, if I want to have the fixed point of the square root, if we can see that type system says to me that we can find it. Now let's imagine that we have no recursion definitions in our language in Haskell, and we have only y combinator, where is no we can't do the recursion. When they define function, they can't do the recursion. And in this way, how can we define the factorial function? Okay, let's try. Let's go into multi-line mode, and I define factorial function in a such way. So my factorial function in the case of it takes some number. Okay, we know that it takes some number. Okay, I don't need multi-line mode. Let's quit for a moment. we know that this function takes some number and what logic it has. So we can say that if our number is equal to 0, then we can define the factorial as 1. Otherwise, we can say that factorial is n multiply by factorial of n minus 1. In such way. But booms, they have this, the problem that they have no, we say that they have no recursion, but I use recursion here. What to do? What we can do? Okay, let's, because we can't do the recursion, we must remove this factorial. We can reference to ourselves. And I remove it, and I have this f here. But what is the f? I have no f from in this context. So let's add it. If we have no it, let's add it here. What now we have some definition, and we must the one problem that this thing that we must from somewhere receive this f. Okay, of course this will not work, and now let's just try to redefine this function that in this way that it compiles. It will compile. Okay, so we understand that they need not one argument to our factorial, they need 2 arguments now, and this one more strange f argument need to us. Now let's define our factorial function in such way. We will receive f function, and in the pattern we use pattern matching. If we use the 0, we say that factorial from 0 is 1. Actually, we have no interest in the f function in this case. And if otherwise, if they have some number, so we do the following. They define it as a n multiply f of n minus 1 in such way. Can we have such a definition? Yes, it works, as you can see. What we have here? They have some function factorial which takes from some function from t to t and produce to us the function from t to t. But let's look here again. What we have here? So we have this such y combinator with the following type signature. Can they use it in this way? This strange fuck function. Okay, now let's just redefine it here somewhere. So I have this y combinator definition, and let's look at its type signature. So now we can see that they can combine fuck and y combinator. If I combine that, what I will receive? You can see that they receive the some function from t to t, and interesting that it has the numeric type constraint, type class constraint. This type has, and they can also it has the equality type constraint. This looks like a factorial? just let's redefine it as a normal factorial. I guess that it is a normal fuck. And if I apply to this, so we can see that it's look like a normal factorial function. Yes. And if I apply to it some number, for example, number 5, you can see that it gives me a factorial. Believe me or not, but it always will give you factorial. And actually what we do, as I say earlier, using this y combinator function, simple function, how many chars? I think here 7 characters. And in our language, we now can be without recursion in an explicit way when they can refer to itself. But this simplest function, they can do any recursion function with such similar reasoning about the recursive programs as we do here. They just in the place of the refer to itself, we just provide some function f as an argument, and then we put all these things into the y combinator, and we will receive the normal recursive function.